This video is on de Moivre's theorem. So recently we looked at a rule for dealing with the product of complex numbers in polar form. So if z1 equals r1 cos a plus I sin a, and z2 equals r2 cos b plus I sin b, then z1, z2 equals r1, r2 cos a plus b plus I sin a plus b. So basically we're multiplying the moduli, r1 by r2, and we're adding up the angles a and b. Don't forget the angles can be called the argument of the complex number. And de Moivre's theorem builds on this. So in our rule that I've written down here, I've just used two complex numbers to multiply together. But de Moivre allows us to multiply a whole load of complex numbers together. Or I suppose more particularly, it allows us to multiply one complex number by itself repeatedly, but in a much quicker way. So if you're multiplying something by itself repeatedly, what's that then? That's putting an exponent on the complex number. So de Moivre is just taking this rule that we've seen for the product of complex numbers in polar form, and it's allowing us to apply powers to complex numbers in polar form. So here's our rule for de Moivre. If z is equal to r cos theta plus I sin theta, then z to the n equals r to the n cos n theta plus I sin n theta. So where does this come from? Well, let's look back to our rule again. If we're multiplying, then we're multiplying our moduli. So what I'm doing is I'm putting z, my complex number, to the power of n. So I'm multiplying it by itself n times, which means that I must be multiplying r by itself n times. So I'm putting a power on the modulus. And if I have z to the power of n, well then I'm adding up n lots of theta. So n lots of theta makes n theta. So we're multiplying the argument by the power. So let's look at an application of this now. So I've got a complex number z, and it's equal to 2 cos 30 plus I sin 30. So it's already in polar form, which makes things kind of handy for me. And I want to find z to the power of 4. So I'm going to reference this rule up here, de Moivre's theorem. So let's see, what am I going to do? I'm going to take my modulus and put it to the same power. And then I'm going to multiply my argument, or my angle, by the power. So z to the power of 4 equals 2 to the power of 4. So I'm putting the power in there on the modulus. Cos 4 times 30 plus I sin 4 times 30. So I'm taking that power and I'm multiplying it by the argument. And of course, I want to resolve this and tidy it up a little bit. And I end up with z to the power of 4 equals 16 times cos 120 plus I sin 120. So that's a really basic example. I'm literally just applying the rule, de Moivre's theorem, without any extra bits at all. So let's look at a second example now that has a little bit more to do. Okay, so in this example, I'm given a complex number. So it's minus root 3 minus I, and I want to find z cubed, but I want to find it in the form a plus bi. Right, the minute I see a power on a complex number, I know the best plan is to go into polar form. And in order to do that, I should start off by drawing a sketch of my complex number z. So there's my z, it's in the third quadrant. So I'm expecting in a while that its argument will be somewhere between 180 and 270, or pi and 3 pi over 2. So I've drawn in its modulus, which I can call r, and I've identified its argument, which I'm going to call theta. And I'm going to drop a line then to the real axis to identify my triangle. And of course, I know the sides of that triangle then, and I'll write them as positive values because obviously I'm talking about distances there. Now, theta isn't in that triangle. So what I'm going to do instead is I'm going to find this angle here, which I'm going to call alpha. And I'm going to add that on to the 180 degrees up as far as this point here. But first of all, the modulus. Don't forget our formula for modulus is the root of a squared plus b squared. So in this case, the modulus of z is the root of minus root 3 squared plus minus 1 squared. And that comes out as 2. And then next job is the argument, the angle. So tan of alpha is 1 over root 3. And the tan inverse of that comes out as 30. So that means that my alpha angle is 30. Don't mix up this angle with the argument, because obviously I've had to come much further than 30 degrees to get the whole way from the positive real axis around as far as that modulus. So I have alpha, but I still have to get theta. So theta, or the argument of z, which can be written as arg z, is 180 plus that 30. So I come out at 210 degrees. So my complex number in polar form, is 2 cos 210 plus I sine 210. Now I've done it in degrees. You can do it in radians as well, and you will encounter radians quite a bit again, like I've said before in this chapter. So make sure that you're familiar with them. Right, I'm not done yet. I have to get z cubed. And that's the reason that I've gone into polar form, because now that I'm in polar form, I can use de Moivre's theorem to apply that power of 3. So there's my formula again, just as a reminder. And this is on page 20 of your log tables, so you can look it up there if you need to. So we're looking for z to the power of 3. So we'll have to say our modulus, which is 2, and we're going to put that to the power of 3. And then we're going to say 3 times our angle. So cos, and we'll say 3 times 210 plus I sine 3 times 210. And then a bit of a tidy up is required. So I end up with 8 cos 630 plus I sine 630. And then, of course, if I look back to the original question, it asked me to give my answer in the form a plus bi. So it's important that I follow that instruction at the end of the question. And that's very easily done just using my calculator. And when I type in the cos of 630, I get an answer of 0. And when I type in the sine of 630, I get an answer of -1. So a little bit of a tidy up, and then my final line is 0 minus 8i. So just to understand geometrically how this answer works, if we look back to our original diagram, notice that the modulus, and this is kind of referring back to earlier videos and just the geometrical effects of multiplication of complex numbers, the modulus of that original z was 2. So if I'm putting it to the power of 3, I'm saying 2 by 2 by 2 with the modulus. So I'm ending up with a modulus of 8. Now I can't represent that in this diagram because obviously 8 is going to be way out here. And I'm looking down particularly here because it's -8. But why would it be on this axis at all? Well, let's have a think about what's happening with the argument again when I'm multiplying my complex numbers together. So my original complex number, my first z, if you like, takes me from the real axis around as far as the modulus. Multiplying by subsequent z's, assuming z is still the same z, is going to continue that rotation. So for every extra z, I'm going to make an extra rotation of the same argument. So my argument there is 210 degrees. So if I multiply by z, I'm going to bring myself around an extra 210 degrees. And if I did that, I'd end up somewhere out in the first quadrant. But I didn't have just z by z. I had z by z by z because it was z cubed. So once I've got to that point, I have to multiply by z again, and I have to perform a further rotation of 210 degrees. And when I perform that rotation, I can see that it brings me around to here, which is in line with the negative imaginary axis. So 630 degrees from the positive sense of the real axis has brought me around to z squared, z cube's argument, and then a distance of 8 out from the origin. So let's just finish up with an easy example. Z equals to cos pi over 4 plus I sine pi over 4. And I want to find z to the power of 5 in the form a plus bi. And the reason that I picked this example in particular was because you can see the way the complex number is written. It looks like there isn't a modulus. So it's just cos pi over 4 plus I sine pi over 4. But every complex number has modulus. So if there isn't one written in, you can assume that the modulus is 1. So I want to find z to the power of 5. So I'll put my modulus to the power of 5. Now, just to point out, by the way, obviously, if I'd left the 1 out, it wouldn't really make much of a difference because 1 to the power of 5 is just going to give me 1 in a second anyway. And then I have cos 5 times pi over 4 plus I sine 5 times pi over 4. A little bit of a tidy up. And I end up with 1 cos 5 pi over 4 plus I sine 5 pi over 4. Again, just a quick reference to the geometric implications of this power of 5. The modulus is 1. So if I multiply the modulus of each subsequent complex number in this multiplication by the previous, I'm just going to still end up with 1. Basically what I'm saying is 1 to the power of 5 is 1. So I'm not going to push my complex number, my resulting complex number z to the power of 5 any further out from the origin than that original complex number was, because don't forget, the resulting modulus is dependent on the multiplication of the moduli of all the complex numbers that are going together in the calculation. And with relation to the argument, you can see that the original angle was pi over 4. And of course, if I'm putting z to the power of 5, I'm doing all those extra pi over 4 rotations, and there's 5 of them. So, of course, I'm going to end up at 5 pi over 4. That's just my 5 rotations of pi over 4. Anyway, to end up with my final solution, I want to get it in the form a plus bi. I can go to my calculator. And cos 5 pi over 4 is minus 1 over root 2 plus I times minus 1 over root 2. And so on my final tidy up then, I end up with z to the power of 5 equals minus 1 over root 2 minus 1 over root 2 I.